Hello, and welcome to Somniora Mind. I'm glad you're here. Here's a paradox to carry into tonight's long, slow drift. Everything you're about to hear happened, in some sense, a very long time ago, and yet it's arriving in your mind for the very first time, right now, tonight. So here are 3 quiet questions to fall asleep inside of. Why is looking up at the night sky the closest thing we have to genuine time travel? Why does the emptiest looking patch of space turn out to be humming with motion the moment you actually look closely? And what does it mean that the calcium in your own bones was forged inside a star that died before this planet ever existed? Here's where we begin, with a fact worth sitting inside of. There are more stars scattered through the observable universe than there are grains of sand on every beach and desert on Earth combined. Let that settle for a moment. Not just a great many. More than every visible grain on every shoreline, every dune, every stretch of desert this planet has ever held. Tonight, we're going to drift slowly through that number and everything folded inside it. Planets without suns, stars that spin hundreds of times a second, galaxies quietly colliding in total silence, and the small, patient forces that built every one of us out of stardust. Get comfortable. Let your shoulders soften into whatever is holding you. Let your breathing slow into something long and unhurried. This is a long, gentle road tonight, so there's no need to rush any part of it. When you're ready, let's lift off. Let's start at the very beginning, with the moment everything we're about to explore first came into being. The universe didn't begin as an explosion detonating inside some pre-existing empty room. There was no outside darkness patiently waiting for matter to come rushing in. Instead, the room itself began to grow. Space expanded outward from an unimaginably hot, dense state, carrying energy, light, and the earliest seeds of everything along with it. In those first instants, conditions were far too extreme for atoms, stars, or planets, or even ordinary light, to exist in any form we'd recognize today. It was a rushing sea of particles and radiation, shifting faster than the mind can comfortably picture. As that expansion continued, everything gradually cooled, and tiny differences in density began to genuinely matter. Those faint, uneven patches would eventually become galaxies, stars, and entire worlds. So when we talk about the beginning of the cosmos, we're really talking about the birth of distance itself, the birth of time, of structure, and of every possibility that followed. Space didn't fill up with a universe. Space becoming a universe was the beginning. Every single atom in your body was forged inside a star, long before this planet ever existed. The calcium in your bones, the iron carried in your blood, the oxygen filling your lungs right now, none of it was made here on Earth. It was created through cosmic processes that unfolded ages before our solar system ever formed. The lightest elements appeared in the universe's earliest moments, but most of the heavier ones required the crushing furnaces found deep inside stars. Atoms fused together there under immense heat and pressure, layer after layer, and when massive stars eventually reached the end of their lives, they exploded outward, scattering those hard-won ingredients across space. Later, that enriched material gathered into new stars, new planets, oceans, rock, and eventually, living things. You were never separate from the universe, simply looking up at it from below. You're made from its earlier chapters. Every heartbeat you'll have tonight depends on matter that once burned inside a distant sun, then drifted quietly through space for ages before finally becoming part of a living body. Looking out into space, in a very real sense, means looking backward through time. Light doesn't arrive instantly, no matter how fast it travels. Even moving at its incredible speed, it still needs real time to cross the distances between worlds, between stars, between entire galaxies. The moon appears to you as it looked just over a second ago. The sun appears as it looked more than 8 minutes ago. A star sitting hundreds of light years away is showing you a version of itself from centuries in the past. With sufficiently powerful telescopes, astronomers can look so far across space that they see galaxies exactly as they existed billions of years ago, back when the universe itself was younger and considerably more crowded with newborn stars. This makes astronomy almost unlike any other science practiced on Earth. The sky was never simply a place. It's a record. Every distant point of light is a message that left its source long before it ever reached your eyes tonight. Near a black hole, gravity becomes intense enough to slow time almost to a complete standstill. This isn't a trick of perception or some strange rounding error. It's a real, measurable effect predicted by relativity and confirmed in gentler forms even here near Earth. The closer an object gets to a genuinely strong gravitational field, the slower its own clock runs, compared to a clock sitting farther away. Around a black hole, this difference can grow extreme. To a distant observer, something falling toward the edge may appear to fade and freeze in place, its light stretching and dimming the whole time. For the object actually falling, though, time continues on entirely normally the whole way down. This strange split reveals something genuinely important. Time was never one single, universal rhythm, shared identically everywhere at once. It bends with gravity. It stretches with motion. It behaves differently depending on exactly where you happen to be standing in the universe. Most of the universe, remarkably, is made of something we simply cannot see at all. Everything familiar, stars, planets, gas, dust, people, even light itself, appears to make up only a small fraction of the total cosmos. The rest is dominated by two genuine mysteries. One is dark matter, which doesn't shine, absorb, or reflect light in any ordinary way. We know it's there because galaxies rotate as though they're held together by far more mass than we can actually see, and because it visibly bends the light of distant objects through gravity alone. The other mystery is dark energy, which appears to be connected directly to the accelerating expansion of space itself. Together, these two hidden components shape the universe on its very largest scales. It's a genuinely humbling thought. Nearly everything we study directly turns out to be only the visible edge of a much deeper reality, quietly moving behind the scenes the whole time. Let's rest here a moment. Breathe in slowly for a count of 4. Hold it. Let it go, slower than it came. Somewhere out past the edge of what any telescope can see, more universe is very likely still unfolding patiently in the dark. Let's turn now toward our own solar system, because even our nearest neighbors still hold plenty of quiet surprises. Not every planet in the universe belongs to a solar system at all. Some drift alone through interstellar space, entirely untethered from any sun. They may have originally formed around a star, only to be flung away later by a gravitational encounter with a larger planet or a passing star. Others may have formed directly from a collapsing cloud of gas and dust, closer to a tiny failed star than an ordinary planet. Without any sunlight at all, their surfaces would be unimaginably cold. And yet some might still hold on to internal heat left over from their own formation, from radioactive decay, or from a thick, insulating atmosphere. A few might even hide a buried ocean beneath a crust of ice. These rogue planets are a quiet reminder that space isn't only filled with orderly systems and neatly circling worlds. It also holds lost wanderers, moving endlessly through the dark between stars, each one carrying its own sealed, private history into the endless night. Even our own galaxy is quietly colliding with a smaller one right now. The Milky Way may seem calm from the inside, but it's surrounded by smaller companion galaxies being slowly stretched and absorbed by gravity. One of them, a small dwarf galaxy, is already being torn apart as it passes through and around our own. Its stars aren't crashing into ours like sparks flying off a fire. Space is simply too empty for that to happen often. Instead, the collision unfolds slowly, vastly, almost ghost-like. Streams of stolen stars arc gently around our galaxy, like faint trails left behind by an ancient visitor. Encounters exactly like this one help build the Milky Way over time, adding stars, stirring gas, and reshaping structure across billions of years. Our home galaxy was never really finished. It's still feeding, still growing, still changing, through mergers that unfold almost too slowly for any single human lifetime to notice. Even the moon itself is slowly drifting farther away from us. Each year, it moves outward by roughly the width of a few fingernails. The cause is hidden in the tides. As Earth rotates, ocean water gets pulled by the moon's gravity, creating tidal bulges that don't line up perfectly beneath it. Because Earth spins faster than the moon actually orbits, those bulges tug the moon gently forward. That small gravitational pull gives the moon a little extra energy and gradually pushes it outward over time. At the same time, Earth's own rotation slows by a tiny amount in return. Long ago, the moon sat much closer, and tides were considerably stronger. Far in the future, it will appear noticeably smaller in the sky than it does tonight. This slow separation is a quiet reminder that even the most familiar relationship in the entire night sky is still changing, measured not in drama, but in patience. Space itself was never truly empty, either. It hums, quietly, with invisible fields and particles. Between planets and stars, there's no air to carry sound the way we understand it, but that doesn't mean nothing is there at all. Space contains thin gas, drifting dust, magnetic fields, radiation, and streams of charged particles thrown off by stars. Even regions that seem entirely vacant can hold faint traces of matter, spread out across enormous distances. Quantum physics adds an even stranger layer on top of that. What we call empty space is filled with fields that can fluctuate, interact, and even give rise to particles under the right conditions. Around Earth, invisible magnetic shields guide charged particles into shimmering auroras. Between entire galaxies, tenuous material stretches quietly through the cosmic web. The emptiness of space was never a simple void. It's a restless stage where forces pass, light travels, particles drift, and the universe quietly continues its work. The sun itself loses millions of tons of mass every single second. It looks perfectly steady from here on Earth, and yet it's constantly transforming itself into pure light. Deep in its core, hydrogen atoms fuse into helium under crushing pressure and enormous heat. A tiny amount of mass is lost in every single one of those fusion reactions, and that missing mass becomes energy instead. It streams outward through the star, slowly making its way to the surface, then finally flies out into space as sunlight. By the time it reaches Earth, it warms oceans, dries weather, feeds plants, and makes nearly every familiar form of life here possible at all. The scale is genuinely astonishing. Every second, the sun converts millions of tons of its own substance directly into energy, and it still has enough fuel left to keep shining for billions more years. Its brilliance was never simply a surface flame. It's matter, quietly becoming light, in the heart of a star. Jupiter, meanwhile, is so massive it nearly became a star in its own right. It's often called simply a planet, but it's really a giant world that hints at something considerably larger. It contains more mass than every other planet in the solar system combined, and its gravity is strong enough to shape much of the surrounding solar system. And yet it never gathered quite enough material to ignite the nuclear fusion that powers a true star. Deep inside, immense pressure squeezes hydrogen into strange forms, including metallic hydrogen, which can conduct electricity and helps generate Jupiter's enormous magnetic field. The planet actually gives off more heat than it receives from the sun, leftover warmth from its own formation and slow contraction over time. If the early solar system had provided far more gas, Jupiter might have become something closer to a small star of its own. Instead, it remained a colossal planet, quietly guarding its own moons, storms, and mysteries beneath its banded clouds. Saturn's rings, despite how grand they look from a telescope, are actually thinner than most people ever imagine. They stretch wide enough to span an enormous distance around the planet, and yet their thickness is surprisingly small compared to their width. In many places, the ring system is only tens of feet, or perhaps a few stories, thick. It's made from countless icy particles, ranging from tiny grains all the way up to chunks the size of boulders, all orbiting Saturn together in a delicate, flattened disk. The rings aren't solid, and they aren't perfectly permanent either. Gravity from nearby moons shapes gaps, waves, and gentle ripples throughout them. Over time, ring material slowly falls into Saturn itself, almost like a kind of icy rain. What looks eternal from a distance may actually be temporary on a truly cosmic timescale, a magnificent feature we happen to be lucky enough to see while it still shines. On Venus, time behaves in a way that feels almost turned inside out. The planet rotates so slowly that a single full turn on its axis takes longer than its entire trip around the Sun. Even stranger, it spins in the opposite direction from most other planets, meaning the Sun there would actually rise in the west and set in the east, somewhere beneath its thick, churning clouds. The surface itself stays hidden under a crushing atmosphere rich in carbon dioxide, where the pressure is intense and temperatures run hot enough to melt lead outright. Its unusually slow rotation may have been shaped by ancient collisions, tidal forces, or simply the drag of its own dense atmosphere over time. Venus is nearly the same size as Earth, and yet its rhythm is utterly alien. It's a quiet reminder of how two neighboring worlds can begin with real similarities and still end up as profoundly different places. Mercury, the closest planet to the Sun, quietly hides ice inside permanently shadowed craters near its poles. That sounds almost impossible for a world so close to such intense heat, and its daylight side truly does bake under extreme temperatures. But near the poles, certain deep crater floors never receive any direct sunlight at all. Because Mercury has almost no atmosphere to spread heat around, those shadowed places remain intensely cold, even this close to the Sun. Over long stretches of time, water molecules delivered by comets, asteroids, or perhaps internal processes may have migrated into these dark traps and simply frozen there. Radar observations and spacecraft measurements have revealed bright deposits consistent with genuine water ice. This makes Mercury a genuine world of sharp contrasts, one landscape scorched relentlessly by sunlight, while nearby shadows quietly preserve frozen material for ages. Even a seemingly burnt world, it turns out, can keep cold secrets tucked away in places the Sun simply never reaches. Mars, cold and dry today, once had rivers, lakes, and quite possibly an entire northern ocean. its surface still carries the traces of a considerably wetter past. Spacecraft have photographed branching valleys, dried lake beds, ancient river deltas, and minerals that typically only form in the presence of liquid water. Some ancient regions look as though streams once flowed across them for long, sustained periods of time. Other evidence suggests a large body of water may have covered parts of the northern lowlands, although scientists still debate the finer details. The planet lost much of its atmosphere over time, which made stable surface water increasingly difficult to maintain. But the old terrain remains, almost like a fossilized memory. Mars was never always the desert we see today. It may once have had shorelines, storms, and moving water beneath a considerably thicker sky, which makes it one of the most compelling worlds in the entire search for ancient habitability. Uranus spins sideways, almost as though something knocked it clean over. Most planets rotate with their poles roughly upright, relative to their path around the Sun. Uranus is genuinely different. Its axis is tilted so dramatically that it essentially rolls around the Sun on its side. This gives the planet extraordinarily extreme seasons, with each pole spending decades pointed either directly toward or directly away from the Sun. One leading idea suggests a massive impact early in its history knocked Uranus into this strange position outright. Another possibility involves complex gravitational interactions with other bodies before the solar system fully settled into its present shape. Whatever actually happened, it left behind a world with pale blue clouds, faint rings, and moons that all follow its own tilted orientation. Uranus was never simply another distant ice giant. It's a genuine clue to the violent early history of planetary formation, back when collisions could rewrite the fate of entire worlds. Neptune, meanwhile, carries winds faster than the speed of sound. It receives only a tiny fraction of the sunlight that warms Earth, and yet its atmosphere remains astonishingly active regardless. Clouds race through its blue skies at speeds that can exceed the speed of sound here on Earth, among the fastest winds ever measured anywhere in the entire solar system. The exact energy behind them still isn't fully understood, though Neptune radiates more internal heat than it actually receives from the Sun, and that extra heat may help stir its atmosphere from within. Methane in its upper air absorbs red light, giving the planet its striking, deep blue color. Dark storms can form and vanish there, some large enough to be seen clearly by passing spacecraft and powerful telescopes alike. At the very edge of the planetary realm, where sunlight runs weak and cold dominates everything, Neptune simply refuses to stay still. It's distant, frozen, and violently alive with weather all at once. And Pluto, when it was finally visited up close, revealed mountains genuinely made of water ice. When the New Horizons spacecraft flew past it, it showed a world far more complex than a simple frozen rock. The surface revealed bright plains, dark regions, hazes, glaciers, and rugged mountains. Some of those mountains are made specifically of water ice, which behaves almost like hard bedrock in Pluto's extreme cold. On Earth, water ice can melt in the palm of your hand. On Pluto, it can stand tall as an entire mountain range. Softer ices, like frozen nitrogen, flow more like glass across broad, open plains. One famous heart-shaped region contains a smooth basin that appears geologically young, filled with cells of slowly churning ice. This distant dwarf planet genuinely surprised nearly everyone who studied it. Instead of being dead and plain, it turned out to be layered, active, and strange. Pluto proved, quite convincingly, that even small worlds at the very edge of sunlight can hold landscapes of genuine, breathtaking complexity. Let's rest here a moment. Let your own breathing slow the way a distant planet turns, patiently, in no hurry at all, held gently by forces far larger than itself. Let's drift now toward the moons and smaller bodies scattered through our solar system, because some of the strangest worlds we know aren't planets at all. Saturn's largest moon, Titan, has rivers and lakes filled not with water, but with liquid methane. It carries a thick atmosphere, an orange haze, real weather, dunes, river channels, and open lakes. But its entire cycle runs on chemistry rather than water at the surface. Titan is so cold that methane and ethane can exist as genuine liquids there. They fall as rain, carve channels through the landscape, gather in lakes, and evaporate back into the sky, over and over. From above, some of its polar regions look almost familiar, with shorelines and dark liquid bodies spread across the landscape. Beneath its icy crust, Titan may also hide an entire ocean of liquid water, mixed with other compounds. This makes it one of the most genuinely intriguing places in the whole solar system. An entire set of Earth-like processes, quietly running on alien materials. On Titan, chemistry writes its own version of weather, where the rivers are hydrocarbons and the rocks themselves are made of water ice. Jupiter's moon Europa may hide a genuinely salty ocean beneath its own frozen shell. From a distance, it looks like a cracked white sphere crossed by reddish-brown lines. Beneath that frozen exterior, though, many scientists think there's an entire global ocean of liquid water. Tidal forces from Jupiter, along with nearby moons, flex Europa as it orbits, creating internal heat that may help keep that water from freezing completely solid. The surface cracks and shifting ice patterns strongly suggest real movement happening from below. If that hidden ocean ever touches a rocky seafloor, chemical reactions there could provide a genuine energy source, much the way they do around deep-sea vents here on Earth. That particular possibility makes Europa one of the most exciting places to investigate for habitability anywhere in the solar system. It isn't appealing because it resembles Earth on the outside. It's compelling because beneath its ice, it may hold one of life's most essential ingredients, in vast and completely hidden abundance. Saturn's small moon Enceladus genuinely sprays ocean water directly out into space. Scientists were stunned when spacecraft first observed plumes erupting from fractures near its south pole. These geysers release water vapor, ice grains, salts, and organic molecules straight from beneath the surface. That material sprays outward into space, quietly feeding one of Saturn's fainter rings and offering a direct sample of the moon's interior without ever needing to drill through the ice at all. The evidence points toward a subsurface ocean in genuine contact with a rocky core underneath. That contact matters enormously, since rock and water can exchange chemistry there, creating conditions that may support genuinely complex reactions. Enceladus is small, bright, and frozen from the outside, and yet beneath its crust, it may be warm enough for liquid water to persist regardless. Very few worlds feel quite so secretive and quite so generous at the very same time. It hides an entire ocean and then sends small pieces of it directly up into the sky. Jupiter's moon Io is the most volcanically active world we currently know of anywhere. It's constantly pulled and squeezed by gravity. Jupiter tugs it steadily one way, while nearby moons help keep its orbit slightly stretched at the same time. This repeated flexing generates intense internal heat, and the result is a surface covered in volcanoes, lava flows, and sulfur-rich deposits. Some eruptions there launch material hundreds of miles above the moon's surface. Unlike Earth's own volcanism, driven largely by internal heat and plate tectonics, Io's activity is powered specifically by tidal forces instead. Its surface changes remarkably quickly, with new deposits regularly covering older terrain. The colors can appear yellow, orange, white, and black, since sulfur and other volcanic compounds continuously paint the landscape. Io shows that a moon doesn't need to be especially large to be geologically fierce. Caught in the grip of a genuinely giant planet, it becomes a restless, volcanic world in its own right. Ganymede, another moon of Jupiter, is actually larger than the planet Mercury. It's still technically a moon, but its size genuinely belongs in planetary conversation. It's the largest moon in the entire solar system, bigger than Mercury and only slightly smaller than Mars itself. Orbiting Jupiter, it has a surface of ice and rock marked by bright grooves, darker ancient terrain, and old impact scars. Even more remarkably, Ganymede has its own magnetic field, something no other known moon can claim in quite the same way. Beneath its crust, there may be layers of liquid water sandwiched between different forms of ice entirely. Its interior is differentiated, meaning heavier material sank inward while lighter material rose outward over the course of its long history. Ganymede was never simply a satellite circling a larger body. It's a complex world in its own right, with geology, magnetism, and a possible hidden ocean, all woven directly into its own story. Neptune's largest moon, Triton, orbits its planet backward. Unlike most large moons, Triton moves around Neptune in the opposite direction to the planet's own rotation. That unusual backward orbit strongly suggests it never actually formed there at all. Instead, Triton was likely captured from farther out in the solar system, perhaps from a population of icy bodies drifting beyond Neptune. That capture would have been a genuinely dramatic event, likely disturbing or destroying whatever earlier moons existed as Triton settled into its new orbit. Today, it's a cold world with a thin nitrogen atmosphere and geyser-like eruptions that may send dark material streaking across its surface. Its orbit is slowly changing too, and far in the future, it may drift close enough for Neptune's gravity to tear it apart entirely, possibly forming a new set of rings in the process. Triton feels almost like an adopted world with a genuinely turbulent past, carrying the chemistry of distant origins, while circling a planet that claimed it, quite literally, by force. The asteroid belt, contrary to how it's often pictured, is mostly empty space scattered between distant rocks. Science fiction often shows asteroid fields as crowded obstacle courses, but the real belt is enormously spread out. It lies between Mars and Jupiter, and although it contains millions of individual objects, the distances between them are usually vast. A spacecraft can pass straight through without ever needing to dodge a single rock along the way. The belt likely contains leftover building blocks from the early solar system that never quite managed to form a planet, partly because Jupiter's gravity stirred the region too strongly for that to happen. Its objects range from tiny fragments to genuinely large bodies, some rocky, some metallic, some containing carbon-rich material that may still preserve ancient chemistry. The belt was never a failed planet in any simple sense. It's closer to a preserved construction yard, quietly holding clues from the era when worlds were still actively being assembled. Ceres, the largest object in that same asteroid belt, may contain more water than many icy worlds combined. It's unusual enough to be classified as a dwarf planet in its own right. Spacecraft observations have revealed bright salt deposits, clay minerals, and clear evidence that water played a genuinely important role throughout its history. Beneath its surface, Ceres may contain a mixture of rock, ice, salts, and possibly briny liquid pockets that have survived far longer than anyone originally expected. Some of its brighter regions appear to have formed when salty material rose up from below and left reflective deposits behind on the surface. This makes Ceres considerably more interesting than a simple asteroid. It sits in the rocky inner solar system, and yet it carries signs of water chemistry more often associated with far colder places. Tucked between Mars and Jupiter, Ceres quietly preserves a record of exactly how water and minerals moved through the young solar system, long before Earth ever took its current shape. Comets, meanwhile, preserve ancient material dating directly back to the solar system's own birth. They're often described casually as dirty snowballs, but they're really closer to frozen archives. They formed in the early solar system out of ice, dust, and organic compounds that happened to remain far from the sun's strongest heat. Many spent billions of years in deep cold, barely changed since the very era when planets were first taking shape. When a comet finally swings close to the sun, its ice is warm and turned directly into gas, carrying dust outward to form a glowing coma and tail. That spectacular display is really only the surface of their true importance, though. Inside, comets preserve chemistry from the solar system's very beginning. Space missions that have visited or sampled them have revealed complex molecules, ancient grains, and real clues about how water and carbon-rich material may have traveled between distant worlds. A comet was never simply a traveler passing through. It's also a genuine time capsule. Halley's Comet has been watched by humans for centuries now. Few objects connect astronomy and human history quite so beautifully. It returns to the inner solar system roughly every 76 years, meaning many generations have watched it pass, each wondering what it might mean. Ancient observers recorded its appearances long before anyone truly understood its orbit. For some cultures, comets were treated as omens. For modern science, Halley eventually became proof that these strange visitors actually followed predictable paths around the sun. Edmund Halley studied earlier sightings and realized they were very likely the same object, returning again and again over time. When it finally reappeared exactly as predicted, it transformed a mysterious sky event into a genuine triumph of celestial mechanics. The comet last visited in the late 20th century and will return again sometime in the 21st. Each appearance quietly links people across time, all watching the very same icy body sweep back in from the outer dark. Meteor showers happen when Earth simply crosses paths with an old comet's trail. A meteor shower can feel spontaneous, almost as though the sky has decided to scatter sparks on its own. In reality, many showers happen specifically when Earth passes through streams of dust left behind by a comet. As those tiny grains enter our atmosphere, they burn up high above the ground and create bright, glowing streaks of light. Most are no larger than pebbles or grains of sand, and yet their speed makes them glow dramatically all the same. Because Earth crosses the same debris paths at fairly predictable times each year, certain meteor showers return like seasonal sky events, connecting us directly to trails of ancient comet material. Each streak was never really a falling star. It's a tiny fragment of cosmic history, briefly made visible as our own planet sweeps through a dusty path around the sun. Let's pause here for the tagline that's become a little ritual of its own on this channel. Because if any of this is helping your mind unwind tonight, and you'd like more of these slow drifts through the strange and the vast, you're welcome to stay a while longer or come back another night. One quiet mind at a time. That's really all this is for. Now, back into the dark and toward human spaceflight itself, because our own small journeys outward carry their own quiet strangeness. The International Space Station circles the entire Earth roughly every 90 minutes. high above the planet, it isn't simply floating in place. It's falling around Earth so fast that it keeps missing the ground entirely. Each orbit carries it across oceans, deserts, cities, storms, and entire night sides lit by rivers of human light below. In a single day, astronauts aboard it experience roughly 16 sunrises and 16 sunsets, meaning their bodies live inside a rhythm unlike anything found on the surface, where morning and evening arrive again and again, faster than the mind can fully settle into either one. The station travels at roughly 17,000 miles an hour, and yet inside, crew members drift calmly through its modules, conduct experiments, repair equipment, and sleep gently strapped in place. It functions as a laboratory, a home, and a lookout post all at once. From up there, Earth becomes a single moving world without borders, turning quietly beneath them in blue and white silence. Astronauts actually grow slightly taller while in orbit, simply because their spines finally get to relax. Here on Earth, gravity presses gently through the body all day long, compressing the spine gradually, which is exactly why people tend to be a little taller in the morning than they are by night. In orbit, that constant downward pull almost entirely disappears. The discs between the vertebrae expand, and the spine itself lengthens as a result. Some astronauts genuinely gain a little height while living in microgravity, though it fades again fairly quickly once they return home. It sounds amusing at first, but it's really part of a much larger story. The human body evolved specifically for weight, pressure, and resistance. Without those familiar forces present, muscles weaken, bones lose density, fluids shift toward the head, and the body's balance systems can become genuinely confused. Space flight reveals just how deeply gravity is written directly into us. Even the shape of the body quietly changes the moment Earth's pull is no longer there to hold it in its usual form. A spacesuit worn outside a spacecraft functions as a tiny spacecraft built specifically around a human body. It's far more than simple clothing. It has to create an entire survivable world in a place with no breathable air, no normal pressure, and extreme swings in temperature. Inside, it provides oxygen, removes carbon dioxide, regulates heat, holds proper pressure around the body, and protects against tiny, high-speed particles. The gloves must stay flexible enough for real tool use, while remaining strong enough to survive the vacuum outside. The helmet provides visibility, while still shielding the face from harsh, unfiltered sunlight. Every joint has to allow real movement, without ever leaking the atmosphere held safely inside. When an astronaut steps outside, the suit essentially becomes a personal life support system, shaped like a person, but functioning like a genuine vehicle. It's engineering wrapped carefully around biology. For a few hours at a time, a human being can leave the shelter of a station or capsule entirely, carrying a small piece of Earth out into space along with them. Rockets themselves work by throwing mass backward with tremendous force. A rocket doesn't push against the surrounding air, which is exactly why it can keep moving even in the total vacuum of space. It moves because of momentum instead. When hot gas blasts out of the engine in one direction, the rocket itself is pushed in the opposite direction. The very same principle you feel when you let go of a balloon and it shoots wildly across a room. The difference here is simply one of scale. Rocket engines burn fuel and an oxidizer together to create a fierce, directed exhaust moving at tremendous speed. The vehicle has to carry nearly everything it will ever need along with it, including the oxygen required for that combustion to happen at all. That's exactly why rockets are mostly propellant at the moment of launch. They're built entirely around the brutal math of escape. To rise from Earth, they have to fight gravity, air resistance, and their own weight all at once, purely by hurling fire downward, again and again. The very first footprint left on the moon may last for millions of years. On Earth, footprints vanish quickly. Wind scatters them, rain softens them, plants grow through them, and rivers slowly erase them, grain by grain. The moon has no weather of that kind at all. There's no rain, no flowing air, and no living surface to gradually cover a mark left behind. When astronauts stepped onto the lunar soil, their boots pressed clear patterns into fine, dusty material, created by countless impacts over billions of years. Those prints remain fully exposed to space, slowly altered only by micrometeorites, radiation, and the faint effects of the solar wind passing over them. They won't last forever, but they may endure for truly immense stretches of time regardless. A single human step became part of the moon's own surface history. Long after the voices from that mission faded from the radio, the marks themselves quietly stayed behind, fragile-looking, and yet strangely permanent, under the black lunar sky above them. Lunar dust, strangely, smells like burnt gunpowder to the astronauts who brought it back inside. The moon itself has no air to carry any scent at all, so astronauts couldn't smell the surface directly while standing outside on it. The real surprise came only after they returned to the lunar module. Fine dust clung to their suits, gloves, boots, and equipment, and entered the cabin right along with them. Once exposed to oxygen and moisture inside, it gave off a sharp smell that several astronauts compared directly to spent gunpowder. The dust itself was clingy and genuinely troublesome too. It was made by endless impacts smashing rock into jagged grains, rather than by water and weather slowly smoothing particles the way it happens on Earth. Those tiny shards could scratch surfaces, irritate lungs, and work their way steadily into seals and mechanisms. That smell was a small, deeply human detail from an entirely alien place. It turned a world of silent craters into something suddenly, strangely immediate, almost as if the moon itself had quietly followed them back inside. Earth's own atmosphere glows faintly when seen from space. From orbit, the planet carries a thin, luminous edge called airglow. It isn't the same as city light or lightning. It comes instead from atoms and molecules high in the atmosphere absorbing sunlight during the day, then slowly releasing that energy back out as faint light. To astronauts, this glow can appear as delicate bands of green, red, or golden color, tracing the gentle curve of the whole Earth beneath them. It reveals something easy to forget from down on the ground. The atmosphere was never a thick shield extending forever upward. It's a genuinely slender layer, wrapped closely around the planet, thin compared to Earth's overall size, and yet utterly vital to everything alive below it. That faint glow marks the boundary between our breathable home and open space. It's beautiful because it's real, but also, quietly, because it shows just how fragile our world's own protective skin genuinely is. Auroras happen when solar particles stir Earth's magnetic field into motion. The sun constantly releases charged particles out into space. Most would be genuinely dangerous if they reached the surface directly, but Earth's magnetic field guides many of them safely toward the polar regions instead. There, they collide with atoms and molecules high in the atmosphere. Oxygen and nitrogen absorb that energy, then release it back out as shimmering light. Greens, reds, purples, and blues can ripple across the sky like curtains, drawn by invisible hands. The display may look soft and gentle, but it's connected to genuinely powerful space weather. Strong solar storms can disturb satellites, radio signals, and power systems here on Earth. Auroras, in that sense, are both beauty and warning at once. They show that Earth was never truly isolated from the Sun. Our planet sits inside a constantly changing stream of solar material, protected by its own magnetism, and yet still, quietly, touched by the very star that gives us light. Surrounding our entire planet are regions where energetic particles get genuinely trapped by Earth's magnetic field, the Van Allen belts. These zones were discovered early in the space age, when instruments first revealed radiation circling above us in great, invisible belts. Many of the particles come directly from the solar wind, while others form when cosmic rays strike the atmosphere. Once trapped, they spiral along magnetic field lines and bounce steadily between the northern and southern regions. This environment matters quite a lot for spacecraft. Electronics can be damaged, and astronauts have to limit their exposure carefully during certain missions. And yet, these same belts are also part of Earth's own defense system, shaped by the same magnetic shield that helps protect the atmosphere from a direct solar assault. They're invisible from the ground, but they form a vast, restless region wrapped entirely around the planet. Earth was never simply sitting quietly in space. It's wrapped in moving radiation and an enormous magnetic structure the whole time. Satellites can eventually fall from orbit, simply because thin air still exists even that high up. Orbit may seem like a perfect vacuum, but near Earth, it isn't completely empty at all. Even hundreds of miles above the surface, faint traces of atmosphere remain. A satellite moving through that thin gas feels a tiny amount of drag as a result. At first, the effect is almost unnoticeable. Over time, though, it steadily steals orbital energy, causing the satellite's path to gradually shrink. It sinks lower, into thicker air, where the drag increases even further. Without correction, it eventually re-enters the atmosphere and burns up, breaks apart, or falls in controlled fragments instead. Solar activity can make this whole process stronger too, by heating and expanding the upper atmosphere further. This is exactly why engineers track orbits so carefully, and sometimes use small thrusters to boost a spacecraft back up higher. Falling from orbit was never like simply dropping off a shelf. It's a slow, gradual surrender to the last, thin wisps of Earth's own air. Let's rest here again for a moment. Let your breathing settle into its own quiet orbit, slow, steady, in no rush at all to arrive anywhere. Let's turn now toward the stars themselves, because their births, lives, and eventual deaths carry some of the most beautiful physics in the entire universe. Stars are born inside cold clouds of gas and dust, and their birthplaces are never fiery at first. They begin instead in dark, cold molecular clouds, where gas and dust drift together across vast regions of space. Gravity slowly gathers denser pockets within these clouds together. As a pocket collapses, it spins, flattens, and begins heating steadily at its center. That growing core becomes a protostar, hidden behind dusty material that blocks visible light from escaping. Around it, a disk may form, and within that disk, planets can eventually begin to assemble. If the core finally becomes hot and dense enough, hydrogen fusion starts, a new star ignites, and its radiation pushes away some of the surrounding cloud entirely. What began as darkness becomes, quite literally, a source of light. Stars, in this sense, were never simply placed into the universe fully formed. They condense out of cold material, slowly awakening from shadow into brilliance. A star's color, remarkably, reveals its true temperature. When people imagine heat, they often picture red as hottest and blue as cooler. Stars teach exactly the opposite lesson. A red star is actually relatively cool by stellar standards, while a blue star burns at far higher temperatures instead. That color comes directly from a star's surface temperature, which shapes the kind of light it gives off most strongly. Cooler stars glow red or orange. Stars like our own sun shine a warm yellow-white. The very hottest stars blaze blue-white, pouring out intense ultraviolet radiation the whole time. This color was never simply decoration. Either, it tells astronomers about a star's mass, lifespan, energy output, and even the conditions surrounding any nearby planets. With a single glance through the right instruments, a star's shade becomes a genuine clue to its underlying nature. The night sky was never simply sprinkled with random lights. It's written in colors that quietly reveal the hidden heat of countless distant suns. Blue stars burn hotter and die considerably faster than red ones. A massive blue star can look like a symbol of raw power, and in many ways, it genuinely is. Its core burns through fuel at an extraordinary rate, producing intense radiation and powerful stellar winds. Because it carries so much mass, gravity squeezes its core fiercely, which drives fusion even faster inside. The result is brilliance, purchased at a real cost. These stars may live for only a few million years, a genuinely brief life by cosmic standards. Smaller red stars, by contrast, use their fuel slowly and carefully, lasting far longer than the current age of the universe in some cases. The contrast between them is genuinely striking. The very brightest stars are often the shortest-lived, while the dimmest can endure almost beyond ordinary imagination. In space, extravagance tends to burn quickly. A blue star gives the universe one dazzling flare of energy, then races swiftly toward its own transformation, collapse, or eventual explosion. Red dwarfs, on the other hand, may shine for trillions of years. They're small, cool stars, and yet their modest nature gives them an astonishing advantage. They burn their fuel so slowly that many could plausibly last for trillions of years, far longer than the universe has even existed so far. Unlike larger stars, some red dwarfs can mix their hydrogen fuel especially efficiently, allowing them to use a greater share of it over time. They're also the single most common type of star in the entire galaxy, quietly filling space with countless faint, long-lived points of light. Because they're so dim, planets have to orbit unusually close to receive enough real warmth, which can create its own complications, like tidal locking or exposure to powerful stellar flares. Even so, their sheer longevity makes them genuinely fascinating to study. Around these patient stars, time stretches into futures our own sun will simply never get to see. Red dwarfs, in a sense, are the slow lanterns of the entire cosmos. Some stars pulse like a kind of cosmic heartbeat, in steady, repeating rhythms. Not every star shines with perfect, unwavering steadiness. Some expand and contract in genuinely repeating cycles, growing brighter and dimmer in patterns astronomers can measure directly. These pulsating stars change because forces inside them fall in and out of balance. Pressure pushes outward, gravity pulls inward, and their outer layers respond almost like a breathing envelope of gas. Certain kinds, called Cepheid variable stars, are especially valuable because their particular rhythm reveals their true, underlying brightness. By comparing that true brightness with how bright the star actually appears from Earth, astronomers can measure enormous distances across the universe. That means a single pulsing star can genuinely become a cosmic measuring tool. Its light rises and falls, and that pattern helps map the entire universe as a result. What sounds, on the surface, like a simple flicker is really a signal, quietly carrying information about size, distance, and the hidden structure of the heavens. Neutron stars can spin hundreds of times every single second. When a sufficiently massive star collapses, its core can shrink down into an incredibly compact neutron star. If the original star was already rotating, that collapse makes it spin dramatically faster, in exactly the same way a skater spins faster by pulling their arms in close. The result can be almost unbelievable. Some neutron stars rotate hundreds of times per second, packing more mass than our entire sun into a sphere only about the size of a city. Their surfaces are governed by gravity far stronger than anything found here on Earth. Their interiors contain matter squeezed into states we simply cannot recreate in any ordinary laboratory. A single rotation happens faster than a blink of an eye, and yet the object itself is heavier than an entire star. These stellar remnants show exactly what happens when nature compresses matter to its most extreme limits. A dead star can become one of the fastest, densest clocks anywhere in the universe. A single teaspoon of neutron star material would outweigh an entire mountain. Density is genuinely easy to underestimate, since everyday matter is mostly empty space at the atomic level. In a neutron star, that emptiness has been crushed away to an extraordinary degree. Protons and electrons are forced together there, forming neutrons packed together with incredible tightness. The result is matter so dense that even a tiny amount would carry a mass far beyond anything familiar. A single spoonful, if it could somehow be brought here, would weigh billions of tons, though in reality, it could never remain stable outside the star's own crushing gravity. This is matter at the very edge of comprehension. It's not merely heavy in the way lead or stone is heavy. It belongs to an entirely different state, created by stellar collapse, where gravity has simply overwhelmed ordinary atomic structure. Neutron stars remind us that the universe contains forms of matter more extreme than the imagination can comfortably hold. Pulsars sweep beams of radiation across the galaxy like a lighthouse signal. A pulsar is a rotating neutron star with beams of radiation shooting outward from its magnetic poles. If one of those beams happens to sweep across Earth, telescopes detect a regular, repeating pulse, sometimes with astonishing precision. The star itself isn't turning on and off. It's spinning, and its beam sweeps across space again and again as it rotates. Some pulsars are so reliable that they genuinely rival atomic clocks over long periods of time. Their signals let scientists test gravity, study interstellar space, and even search for tiny disturbances caused by gravitational waves passing through. The very first pulsar discovery was so strange that researchers briefly wondered whether the pulses might be artificial in origin. Nature turned out to be the answer, but the truth was no less remarkable for it. A collapsed star, city-sized and wildly dense, can send a steady rhythm across the entire galaxy, arriving here on Earth like a slow, distant heartbeat from deep space. Magnetars, meanwhile, carry magnetic fields beyond ordinary imagination. Some neutron stars possess magnetic fields so powerful that they form their own special class entirely, magnetars. Their magnetism runs trillions of times stronger than anything most people will ever encounter here on Earth. At close range, a field like that would genuinely distort atoms and disrupt ordinary matter altogether. Magnetars can produce sudden flares of high-energy radiation when stress is building in their crust and magnetic field finally release enormous amounts of energy at once. A single flare from one within our own galaxy has actually affected Earth's upper atmosphere, even from a vast distance away. These objects are rare, short-lived, and intensely strange. They're not especially large by astronomical standards, and yet their magnetic influence is almost terrifying in scale. A magnetar shows that after a star dies, it may leave behind not only dense matter and strong gravity, but a genuine magnetic engine, powerful enough to announce itself across thousands of light years. Supernovae can briefly outshine entire galaxies. When certain stars finally die, they don't fade away gently. A sufficiently massive star can collapse and rebound in a genuinely catastrophic explosion, while a white dwarf in a separate system can detonate outright after gaining too much mass from a companion. In both cases, the release of energy can be immense. For days, or even weeks, a supernova may shine brighter than the combined light of billions of ordinary stars within its own galaxy. These explosions are destructive, and yet they're also genuinely creative at the same time. They scatter newly forged elements out into space, stir nearby gas clouds, and sometimes trigger entirely fresh episodes of star formation. The calcium in your bones and the iron in your blood are directly connected to exactly this kind of cosmic violence. A supernova was never only an ending. It's a redistribution of ingredients, a brilliant announcement that one star's death can help prepare the material for entire future worlds. Heavy elements, more broadly, get scattered through space by dying stars. A star spends its entire life making new elements and layers, almost like a furnace with several different chambers. Near the end of its life, the largest stars contain shells of carbon, oxygen, silicon, and heavier materials, all surrounding a dense core. When collapse finally begins, the star can explode with genuinely breathtaking force. The blast throws those enriched layers outward into space, where they mix directly with the gas clouds drifting between stars. Over time, that material becomes part of entirely new star systems. This is how the universe quietly recycles itself. The atoms found in rocks, oceans, air, and living cells were never freshly invented here on any one planet. They're inherited from earlier generations of stars. Death, in this sense, becomes distribution. A stellar ending can seed a future world with chemistry complex enough for mountains, seas, and eventually, life itself. Gold may form specifically when two neutron stars collide. For a long time, scientists genuinely wondered where the universe made many of its heaviest elements. Ordinary stellar fusion simply can't easily build all of them. Then astronomers finally observed the aftermath of two neutron stars spiraling together and merging directly. The event released gravitational waves, light, and a cloud of neutron-rich debris all at once. In that extreme environment, atomic nuclei could rapidly capture neutrons and build genuinely heavy elements, including gold, platinum, and others. The glow from a collision like that is called a kilonova. It's not only a violent merger between two dead stars, it's a genuine cosmic forge, capable of creating real treasure. The gold in a ring, or a tiny fleck within a rock, may have begun inside one of these rare collisions, long before Earth ever existed. Something precious resting on your own hand may be the cold remnant of an ancient star crash. White dwarfs are the glowing remains of dead, sun-like stars. When a star like our own sun reaches the end of its active life, it sheds its outer layers out into space. What remains behind is a dense, hot core called a white dwarf. It no longer produces energy through ordinary fusion, and yet it can continue shining for billions of years, purely from leftover heat. A white dwarf can hold a mass comparable to our entire sun, packed inside a sphere roughly the size of Earth. That makes it incredibly dense, though not quite as extreme as a neutron star. Slowly, it cools and fades, moving steadily toward a darker future. Around some white dwarfs, astronomers have found traces of broken planets and rocky debris, meaning even after a star's gentle death, pieces of its old system may still orbit quietly nearby. A white dwarf was never simply an ember. It's the compact memory of an entire vanished sun. Some dead stars can explode after quietly stealing gas from a nearby companion. In a close binary system, one star can survive as a white dwarf, while another continues to evolve right beside it. If the pair orbits closely enough together, the dense remnant can pull gas directly away from its companion. That stolen material spirals inward and slowly piles onto the white dwarf. If enough mass gathers, pressure and temperature can rise until runaway nuclear reactions finally ignite. The result can be a particular type of supernova, so consistently bright that astronomers actually use it to measure cosmic distances across the universe. These explosions help reveal, in fact, that the expansion of the universe itself is accelerating. The story here is strangely dramatic. A star that seemed entirely finished can return in one final, brilliant flash after quietly feeding off its neighbor. What looks like a quiet remnant can become a genuine cosmic marker, bright enough to help map the entire universe. Betelgeuse, one of the most famous stars in the sky, is a red supergiant nearing the very end of its own life. It's genuinely enormous. If placed at the center of our own solar system, its outer layers could reach beyond the orbit of Mars, or even further, depending on exactly how its shifting surface is measured. It's swollen, relatively cool by stellar standards, and genuinely unstable. Its brightness changes as its outer layers pulse, convect, and steadily release material out into space. One day, Betelgeuse will explode as a supernova. That won't harm Earth at all, since it sits so far away. But it could become spectacularly bright in our own night sky when it happens. Astronomers don't know exactly when this will occur. It could happen soon, in cosmic terms, or far beyond any single human lifetime. Watching Betelgeuse is a little like watching an old giant breathe, quietly aware that its final act is waiting somewhere ahead. Our own sun will one day become a red giant too. It's stable right now, but it won't remain this way forever. As hydrogen in its core gradually becomes depleted, the balance between gravity and outward pressure will begin to shift. The core will contract and heat, while the outer layers expand enormously outward at the same time. The sun will swell into a red giant, becoming considerably larger and brighter than it is today. The inner planets will face extreme conditions as a result, and Earth's surface will no longer be a place for oceans or for familiar life as we know it. This particular future lies billions of years away, but it's genuinely written into the life cycle of every star like our own. The sun was never a permanent lamp. It's a changing star with a genuine beginning, a middle, and an ending. Its own future transformation is a quiet reminder that even the source of daytime is part of a much larger cosmic evolution. After that, our sun will eventually fade into a white dwarf of its own. Following its red giant phase, it will shed its outer layers out into space. Those layers may briefly form a glowing cloud, illuminated for a while by the newly exposed core underneath. What remains behind will be a small, dense, stellar remnant. It will no longer warm the solar system the way it once did. Instead, it will cool slowly, over immense stretches of time, fading gradually from brilliant white to considerably dimmer shades, as its stored heat quietly escapes. Any planets remaining in stable orbits will simply circle a much quieter relic from then on. This isn't a sudden disappearance in any sense. It's a long, gradual decline, measured across time spans far beyond ordinary human history. The final sun will be Earth-sized, dense, and cooling. The star that once powered forests, winds, storms, and oceans will become a small ember, quietly carrying the memory of all the light it ever gave. Stars often form in genuine families, rather than entirely alone. A single giant cloud of gas and dust can collapse into many newborn stars all at once, creating an entire cluster. Some clusters stay loose and young, filled with bright blue stars still burning fiercely. Others become ancient globular clusters, tightly packed with hundreds of thousands of stars and dense, spherical swarms surrounding a galaxy. In young clusters, astronomers can study stars that all formed from the very same material, and yet ended up with genuinely different masses. This makes them natural laboratories for understanding how stellar lifetimes actually work. Over time, gravity and galactic tides can pull a cluster apart entirely, spreading its stellar siblings out through space. Our own sun may well have been born inside just such a group, before gradually drifting away on its own. A star cluster, in this sense, is a genuine cosmic nursery, a gathered generation of suns, all beginning their lives together from the very same cold cloud. Nebulae glow specifically because nearby stars excite the gas within them. Some of the most beautiful objects anywhere in space are vast clouds of gas, lit either from within or nearby. When hot young stars pour out ultraviolet radiation, that energy strikes atoms scattered throughout the surrounding nebula. Those atoms absorb the energy, then release it back out as light, at very specific colors. Hydrogen often glows red or pink. Oxygen can shine a greenish or blue color instead. The result was never painted decoration. It's simply physics, made directly visible. These glowing regions may surround newborn stars, mark places of active star formation, or trace material shed by a dying star. Their shapes are sculpted by radiation, stellar winds, gravity, and sometimes even shock waves passing through. A nebula can be both delicate and genuinely powerful at once, a place where gas becomes luminous, and where new stars may still be quietly forming inside its denser, hidden pockets. Not every cloud in space actually glows, though. Dark nebulae hide newborn stars entirely, behind curtains of dust. Some appear simply as black shapes set against a brighter background, blocking the starlight sitting directly behind them. These dark nebulae are filled with cold gas and fine dust grains. That dust absorbs and scatters visible light, creating silhouettes that can look almost like genuine holes torn in the sky. And yet they're never truly empty. Inside their densest regions, gravity may already be gathering material into a new protostar. Infrared telescopes can peer straight through much of that dust and reveal hidden warmth exactly where star formation is quietly underway. These clouds matter enormously because they show the earliest possible stages of stellar birth, well before any brilliant light manages to break free. A dark nebula was never a dead patch of sky. It's a sealed chamber, cold and obscured, where entirely new suns may be quietly forming behind the veil. Let's rest for a moment here. Let your own breathing slow the way a nebula slowly gathers itself, patiently, over unthinkable stretches of time, towards something bright and entirely new. Let's turn now toward black holes and the strange, beautiful physics that governs the very edges of gravity itself. At the very heart of our own galaxy lies a supermassive black hole, a compact object carrying the mass of millions of suns. We can't see it directly, but we can watch nearby stars whipping around it at truly extraordinary speeds. Their orbits reveal an enormous amount of mass, packed into a remarkably tiny region of space. Radio telescopes have even imaged the hot, glowing material swirling around its dark shadow. Compared to some giant black holes found in other galaxies, ours is actually fairly calm at the moment. It isn't devouring enough material to blaze as a genuine quasar. Still, It anchors the very central region of the Milky Way and offers scientists a genuinely nearby laboratory for studying strong gravity up close. Our own galaxy carries a hidden heart. Around it, stars move like dancers, circling an invisible weight at the center of everything. Black holes, contrary to popular imagination, aren't cosmic vacuum cleaners at all. A black hole doesn't suck in everything around it, simply by virtue of existing. From far enough away, its gravity behaves exactly like the gravity of any other object carrying the same mass. If our sun were somehow replaced by a black hole of equal mass, Earth wouldn't instantly go tumbling in. It would simply keep orbiting, exactly as it already does. Life would lose its sunlight, of course, but the real danger only comes from getting genuinely too close. Near the event horizon itself, gravity becomes extreme, and paths that once led outward can begin curving inward forever instead. Black holes can feed on nearby gas, dust, or an unlucky star, but only material that strays directly into their reach ever actually gets captured. This distinction matters, because it makes black holes considerably more understandable overall. They were never magical drains scattered through space. They're simply regions where mass has been compressed so tightly that escape has become genuinely impossible. Light itself can actually orbit a black hole before finally escaping. Around a black hole, space-time curves so strongly that even light can follow genuinely strange paths through it. At a certain region just outside the event horizon, photons can circle the black hole in unstable orbits of their own, an area sometimes called the photon sphere. A beam of light there sits balanced on a genuine knife's edge. A tiny disturbance sends it either outward into open space or inward toward no return whatsoever. This particular effect helps shape the bright rings and shadows seen in real black hole images. Light from hot gas near the black hole can bend around it, giving astronomers a genuine view into regions that would otherwise remain completely hidden. The idea feels almost impossible, since light usually represents pure straightness and speed. Near a black hole, though, even the fastest thing in the entire universe can be trapped, for a moment, into a curved path. Some black holes are heavier than entire small galaxies. At the centers of many large galaxies sit supermassive black holes, but some of these grow to truly staggering sizes. They can reach billions of times the mass of our sun, meaning a single invisible object can genuinely outweigh every star inside a small galaxy combined. These cosmic giants likely grew by feeding steadily on gas, merging with other black holes, and living for ages in dense galactic centers, where material was genuinely plentiful. When actively feeding, the region around them can release more energy than the entire galaxy hosting them. Their gravity influences nearby stars and gas directly, and their outflows may help regulate exactly how their host galaxies evolve over time. A black hole itself emits no light at all from within its event horizon, and yet its surroundings can become some of the brightest known objects anywhere in the universe. Darkness, under exactly the right conditions, can power astonishing brilliance. Hawking radiation suggests that even black holes may slowly evaporate over time. Classical physics once made black holes seem like one-way traps, capable only of growing larger. Then quantum theory changed that entire story. Stephen Hawking showed that effects occurring near the event horizon imply black holes should actually emit a tiny amount of radiation. For large black holes, this radiation is unbelievably weak, considerably colder than the cosmic background surrounding it. But over immense timescales, if a black hole absorbs less energy than it emits, it could gradually lose mass. Very small black holes would evaporate considerably faster than large ones. This idea links gravity, quantum physics, and thermodynamics together in a deep and still genuinely unresolved way. No one has yet directly observed Hawking radiation from a real astrophysical black hole, but the prediction reshaped how scientists think about them entirely. It suggests that even the darkest objects in existence may not last forever. Their endings would simply be slow, beyond ordinary imagination. Gravitational waves are ripples made by moving space-time itself. When massive objects accelerate, they can disturb the very fabric of space-time around them. The strongest detectable ripples come from extreme events, like merging black holes or colliding neutron stars. These waves spread outward at the speed of light, gently stretching and squeezing space by incredibly tiny amounts as they pass through. By the time they reach Earth, the resulting change is far smaller than the width of a single atom. And yet sensitive instruments can measure it regardless. This discovery opened an entirely new way to study the universe. Instead of only collecting light, scientists can now genuinely detect vibrations moving through space-time itself. It's a little like gaining an entirely new sense, tuned specifically to cosmic events that might otherwise remain hidden. A collision far away can make the universe tremble, and after traveling for ages across the dark, that faint tremor can still whisper quietly through instruments here on Earth. Scientists first detected gravitational waves directly, arriving from two colliding black holes. In 2015, detectors here on Earth recorded a signal unlike anything ever seen before. It came from two black holes spiraling together, more than 1 billion years earlier. As they orbited faster and faster, they released energy as gravitational waves, then finally merged into a single, larger black hole, producing one last ringing signal as they combined. The detection confirmed a major prediction from Einstein's theory of relativity and marked the true beginning of gravitational wave astronomy. Nothing about the event was visible through any ordinary telescope, since black holes themselves don't shine at all. And yet the motion of space-time itself carried the news across the entire cosmos regardless. The signal lasted only a fraction of a second inside the detectors, but it represented a genuinely colossal event. For the very first time, humans hadn't only seen the universe. We had actually heard its deepest structure move. Space-time bends around mass, almost like an invisible cosmic fabric stretched out across everything. Gravity was never only a force pulling objects together in the old familiar sense. In Einstein's description, mass and energy shape space-time directly, and objects simply follow the curves that result from that shaping. Earth orbits the Sun because it's moving through curved space-time, wrapped gently around the Sun's own mass. Light follows these same curves too, which is exactly why massive galaxies can bend and magnify the light of objects sitting behind them, an effect called gravitational lensing. This lets astronomers study distant galaxies, map hidden matter, and even locate certain planets in particular cases. The image of a stretched fabric is only an analogy, but it genuinely helps here. Matter tells space-time how to curve, and curved space-time tells matter how to move and turn. The universe was never a rigid, fixed stage. It's flexible geometry, shaped continuously by everything held within it. Even gravity itself travels only at the speed of light, and no faster. If the Sun could somehow vanish instantly, Earth wouldn't feel that gravitational change immediately either. The change would travel outward at light speed instead, reaching us only after the very same delay sunlight itself would take. This doesn't actually happen in reality, of course, but the thought experiment reveals something genuinely important. Gravity was never an instantaneous command, issued instantly across all of space. It's part of the structure of space-time itself, and changes in that structure propagate only at a finite speed. Gravitational wave detections support this picture directly, especially in one case where a neutron star merger produced both gravitational waves and ordinary light that arrived close together after traveling across a truly cosmic distance. The results showed that gravity and light move at essentially the very same speed through space. Even the most fundamental influences in the entire universe obey the very same cosmic speed limit. Distance matters, not only for light, but for gravity itself as well. Time, remarkably, actually passes slightly faster on satellites than it does here on Earth. A clock in orbit doesn't tick at exactly the same rate as an identical clock down on the ground. Two separate effects are involved here at once. Because satellites move quickly, relativity says their clocks should run a little slower, purely from that motion. But because they're also considerably farther from Earth's gravity, their clocks run slightly faster instead, purely from that distance. For navigation satellites specifically, the gravitational effect turns out to be larger overall, so their clocks actually gain time compared to clocks here on Earth. The difference is genuinely tiny each day, and yet it matters enormously. Without correcting for it precisely, satellite navigation would become inaccurate remarkably quickly. This means relativity was never simply an abstract idea, reserved for black holes and distant galaxies alone. It's built directly into technology people rely on every day for maps, travel, shipping, and timing. Every accurate position a satellite provides depends entirely on understanding that time itself changes with both speed and gravity. Let's pause here for a moment and let your own thoughts settle the way light settles into a gravitational curve, following the shape of whatever surrounds it, without ever needing to fight against it. Let's turn now toward the very beginning of everything and the vast, structured universe that slowly grew out of it. The Big Bang was never an explosion happening inside empty space. It's easy to imagine the beginning as a single blast, occurring somewhere out in the darkness. But that particular picture is genuinely misleading. There was no empty arena, patiently waiting for matter to fill it up. Space itself was expanding instead. Every single region was once compressed into a hotter, denser state, and then distances between everything simply began increasing everywhere at once. This means the beginning never happened at one central point located somewhere in space. It happened to space itself. As the universe expanded, it cooled enough for particles, atoms, stars, and galaxies to eventually emerge from the process. The name itself can make it sound like a firework going off, but the reality is considerably stranger and considerably deeper. It was the unfolding of the very stage on which all later events would happen. Every direction we look carries evidence of that early, hot beginning, stretched across the entire sky, like a memory quietly written into the universe itself. Ancient microwave light, remarkably, still fills the entire universe, even now. Long after that first expansion began, the universe remained filled with hot, trapped light. Photons couldn't travel freely, since they kept scattering constantly off charged particles nearby. Then the universe finally cooled enough for electrons and atomic nuclei to join together into complete atoms. Light was suddenly able to move freely across space for the very first time. And that ancient release is still with us today. It's been stretched by cosmic expansion into faint microwave radiation, arriving from every direction, almost perfectly uniform, and yet carrying tiny temperature differences that reveal the earliest seeds of later structure. Those slight variations help scientists understand exactly how galaxies eventually formed. This particular glow doesn't come from any star. It's older than every star. It's the afterglow of a moment when the universe first became clear, a background whisper from the young cosmos, still quietly surrounding every world, every galaxy, and every observer who happens to be listening. The universe became genuinely transparent only after atoms first formed inside it. For its long first chapter, the cosmos behaved like a glowing fog. Free electrons filled space and scattered light again and again, preventing photons from ever traveling very far. Then expansion cooled everything enough for electrons to finally settle around atomic nuclei. Hydrogen and helium atoms formed, and the fog itself finally lifted. Light could stream freely across the universe at last, without being constantly blocked. This particular moment happened hundreds of thousands of years after the very beginning, and it genuinely changed everything that followed. It gave us the oldest light we can directly observe today. Before it, the universe remains essentially hidden from ordinary, light-based astronomy. After it, radiation could travel freely, carrying real information across cosmic time. The formation of atoms was never simply a chemistry event. It was the exact moment the universe became visible to itself, opening the very first clear window through which its earliest structure could eventually be studied. Galaxies grow, in large part, by merging with smaller galaxies around them. A galaxy is never born complete, and then simply left unchanged forever after. It grows through gravity, collecting gas, stars, dark matter, and sometimes entire smaller galaxies along the way. When a large galaxy captures a dwarf galaxy, the smaller system can be stretched into long streams, its stars scattered out into the halo, and its gas folded directly into future star formation. These mergers can look genuinely violent on grand scales, but individual stars rarely collide directly, since the distances between them remain enormous the whole time. Instead, the overall shapes of galaxies get transformed by gravity. Spirals can be disturbed. Ellipticals can be built through repeated encounters over time. The Milky Way itself carries evidence of past meals, quietly visible in the motions and chemistry of its own stars. A galaxy, in this sense, is more like an unfolding history than a fixed object. Its present shape is really a record of everything it has gathered, disturbed, and absorbed. Andromeda, our nearest large galactic neighbor, is genuinely moving toward the Milky Way right now. Far across intergalactic space, it's being drawn steadily closer by mutual gravity, and in several billion years, the two galaxies are expected to begin a vast, slow merger. The word collision sounds alarming, but stars are so widely spaced apart that direct impacts will remain extremely rare throughout. The real drama will be almost entirely gravitational instead. Both galaxies will stretch, twist, and fling long streams of stars into entirely new orbits. Gas clouds may compress and spark fresh episodes of star formation as a result. Over time, the two great spirals may eventually settle into one larger, more rounded galaxy together. From Earth, if anyone happened to be watching, the night sky would change beyond all recognition. Andromeda was never merely a distant smudge, seen faintly through binoculars. It's the future partner of our own galaxy, already approaching steadily through the dark, with a kind of majestic inevitability. Future astronomers, remarkably, may end up seeing far fewer galaxies than we do tonight. The universe is expanding, and that expansion is accelerating on the largest scales. Over immense stretches of time, galaxies beyond our own local gravitational group will appear to move away faster and faster. Their light will become stretched, dimmed, and eventually impossible to detect at all. A civilization in the far future might look up into the night and see a considerably emptier universe than the one we get to observe tonight. Nearby, already merged galaxies would remain visible, but the wider cosmic web could fade entirely beyond reach. This is a genuinely haunting idea, because our own particular age may be unusually rich for astronomy. We can still observe distant galaxies, ancient light, and direct evidence of cosmic expansion. The universe is offering clues right now that may simply not be available forever. Our telescopes aren't only looking outward tonight. They're looking during a genuine cosmic window, while the broader universe can still be seen at all. Cosmic expansion, meanwhile, stretches old light into redder wavelengths as it travels. As space expands, it carries light along with it the whole way. A photon traveling for billions of years has its wavelength stretched by the growing universe around it. Longer wavelengths correspond to redder light. And for the most distant objects observed, visible light can be stretched all the way into infrared or even microwave radiation. This effect is called cosmological redshift, and it's one of the clearest signs that the universe is genuinely expanding. It also means distant galaxies aren't only far away in simple space. Their light has been changed by the entire history of space itself along the way. Astronomers measure this stretching to estimate distances and to look back into earlier cosmic eras. The farther away a galaxy sits, the more its light has usually been stretched. In that reddening, we're really reading the expansion of the cosmos directly. Every old photon carries a quiet record of the universe growing the entire time it traveled. Dark energy appears to be speeding up cosmic expansion rather than slowing it down. For much of scientific history, many researchers expected gravity to gradually slow the expansion of the universe over time. Galaxies pull on one another, after all, and matter naturally attracts more matter. Then observations of distant supernovae revealed something genuinely surprising. The expansion wasn't slowing, as everyone had expected. It appeared to be accelerating instead. To describe whatever force is driving that acceleration, scientists use the name dark energy. It isn't dark because it's shadowy in any visual sense. It's dark because its true nature remains genuinely unknown. It may be a property of space itself, or it may point toward physics we simply haven't discovered yet. Whatever it actually turns out to be, it dominates the large-scale fate of the entire cosmos. Its influence grows more important across the vast, empty spaces between galaxy clusters. The mystery here is genuinely immense. The universe isn't merely expanding. Something woven directly into its fabric seems to be urging that expansion steadily onward. Dark matter, in turn, shapes entire galaxies without ever giving off a single photon of light. Galaxies rotate in ways that visible matter alone simply cannot explain. Stars far from a galaxy's center move far too quickly to be held in place by the gravity of the stars and gas we can actually observe, unless considerably more mass is genuinely present. This unseen mass is called dark matter. It doesn't shine, reflect, or absorb light in any ordinary way, but its gravity affects everything around it regardless. It forms vast, invisible halos around galaxies and helps guide the growth of cosmic structure at every scale. Without it, galaxies like the Milky Way likely wouldn't have formed in anything like their current form. Scientists haven't yet identified the actual particle or substance responsible for it, but the gravitational evidence keeps appearing again and again, from galaxy rotation to gravitational lensing to the overall distribution of entire galaxy clusters. Dark matter is invisible, and yet it acts like scaffolding. It helps build the luminous universe, while remaining entirely hidden from view itself. The cosmic web links galaxies together through vast, invisible threads stretching across the universe. On the largest scales, galaxies were never simply scattered randomly through space. They gather instead along filaments, sheets, and knots, all separated by huge, largely empty regions. This overall structure is called the cosmic web. Dark matter provides much of its underlying gravitational framework, while ordinary gas and galaxies simply trace its outlines from the outside. At the densest intersections, entire galaxy clusters form. Along the connecting threads, matter flows and gathers steadily over billions of years. Between them lie enormous voids, with far fewer galaxies scattered inside. Computer simulations show that tiny early differences in density could genuinely grow into this vast pattern, purely through the ordinary pull of gravity. When astronomers map millions of galaxies together, the universe begins to resemble a great, interconnected network rather than a smooth spread of scattered lights. The cosmic web is one of the grandest structures known to exist. It means every single galaxy belongs to a far larger architecture, connected across distances so huge they genuinely challenge the imagination. Some galaxies are shaped like graceful spirals, and others like soft, glowing clouds. Galaxies come in many different forms, and each individual shape tells its own particular story. Spiral galaxies have rotating disks, arms rich with gas and young stars, and central bulges filled mostly with older stellar populations. The Milky Way is one of these, with our own sun located far from the center, out in a broad stellar disk. Other galaxies appear genuinely irregular, without any neat shape at all, often because gravity from a neighboring galaxy has disturbed them. Some look like soft, glowing clouds of stars, rounded and gentle, with little obvious internal structure. Shape, in every case, can reveal motion, age, gas content, and overall history. A spiral may still be actively making new stars in its arms. An irregular galaxy may be quietly recovering from a recent encounter. A smooth, cloud-like galaxy may simply be the result of ancient mergers, long finished. Galaxies were never merely islands of light scattered through the dark. Their forms are biographies, written patiently by gravity itself. Elliptical galaxies, in particular, can contain remarkably ancient stars and very little new gas at all. They often appear smooth, rounded, and gently golden in tone, compared to the brighter, bluer star-forming spirals nearby. Many contain mostly older stars, with relatively little cold gas remaining. Without much gas left, they simply can't create large numbers of new stars anymore. Their calm, quiet appearance can hide a genuinely violent past, though. Some may have formed through mergers that thoroughly stirred up stellar orbits, and used up or expelled most of their remaining gas in the process. Others sit at the very centers of galaxy clusters, where they've grown genuinely huge by slowly absorbing smaller neighbors over time. The stars inside move in many different directions, rather than circling neatly within a flat disk. To the casual eye, galaxies like this may look simple. To astronomers, they're genuine fossils of cosmic history. Their old stellar populations preserve real clues about early star formation, past collisions, and the long, slow process by which galaxies gradually age into quieter forms. Quasars are powered by genuinely hungry supermassive black holes. A quasar can shine brightly enough to be visible across billions of light years. The light itself doesn't come from inside the black hole, since nothing at all escapes from within its event horizon. It comes instead from material swirling around a supermassive black hole just before falling in. Gas in that surrounding accretion disk becomes extremely hot as friction, compression, and magnetic forces release tremendous energy. The resulting region can genuinely outshine the entire galaxy surrounding it. Some quasars also launch powerful jets, racing outward at nearly the speed of light. They were considerably more common in the earlier universe, back when galaxies contained far more available gas to feed their central black holes. A quasar, in this sense, is a genuine sign of appetite on a truly cosmic scale. It's a galaxy's own central darkness, surrounded by one of the brightest engines nature has ever produced. Some galaxies blast jets that stretch far longer than the galaxies themselves. In certain active galaxies, material near a central supermassive black hole gets organized by magnetic fields and launched outward in narrow, focused jets. These jets can extend far beyond the visible galaxy entirely, crossing hundreds of thousands or even millions of light years. They're made of energetic particles moving at incredible speeds, often producing radio waves that telescopes can detect clearly from Earth. The black hole itself doesn't shoot material out from inside its own boundary. The jets come instead from the turbulent region surrounding it, where gas, rotation, and magnetic fields all combine together under extreme conditions. These outflows can heat surrounding gas and directly affect whether new stars manage to form nearby. A galaxy may look, in ordinary visible light, like nothing more than a quiet collection of stars, and yet in radio waves, it can reveal enormous structures reaching far out into intergalactic space. Its hidden engine can influence regions far larger than the galaxy's own visible, starlit body. The earliest galaxies formed surprisingly soon after the Big Bang itself. As telescopes have grown steadily more powerful, they've found galaxies from earlier and earlier cosmic times. Some appear even when the universe was only a small fraction of its current age. This genuinely challenges scientists to understand exactly how stars, gas, and dark matter managed to gather so quickly into organized systems in the first place. The very first galaxies were likely smaller and more chaotic than most modern ones, with intense star formation and far fewer heavy elements present. Their light has been stretched into infrared wavelengths by cosmic expansion, which is exactly why infrared telescopes matter so much for studying them today. These ancient galaxies were never simply nearby objects with ordinary histories. They're genuine messages from the universe's own youth. Seeing them helps astronomers investigate exactly how the very first star cities formed out of darkness and how their radiation and chemistry changed the surrounding cosmos. Galaxy clusters represent the largest structures ever held together purely by gravity. A single galaxy cluster can contain hundreds or even thousands of individual galaxies bound together within one immense system. Between those galaxies lies hot gas that shines brightly in X-rays, and surrounding the whole thing is a vast amount of dark matter. The galaxies themselves are really only the most visible pieces of the puzzle. The entire cluster forms a deep gravitational well, shaping the motion of everything held inside it. Clusters can bend light from more distant objects behind them, creating dramatic arcs and magnified images through the same gravitational lensing effect we mentioned earlier. They also grow by merging with other clusters, producing collisions so genuinely large that they can reveal dark matter actively separating from ordinary gas as the collision unfolds. On scales even larger than clusters, cosmic expansion can eventually overcome local gravity entirely. But inside a cluster itself, gravity still wins decisively. These structures are, in a very real sense, cosmic cities of galaxies, bound together across millions of light years by shared mass and shared history. Empty cosmic voids can stretch across hundreds of millions of light years. Between the filaments and clusters that make up the cosmic web lie enormous regions with far fewer galaxies scattered through them. These are cosmic voids. They're never completely empty, but compared to crowded clusters nearby, they're astonishingly sparse regardless. A void can be so large that light needs hundreds of millions of years just to cross it. Their existence helps reveal exactly how structure originally formed. Gravity pulled matter steadily toward denser regions over time, leaving the underdense regions increasingly empty in comparison. Over the following ages, voids expanded relative to the surrounding web around them. If a galaxy happened to live inside one, its own night sky might hold far fewer bright neighboring galaxies than ours does. Voids matter because they show that the universe has real texture on its very largest scales. It was never evenly filled throughout. It's a landscape of walls, threads, knots, and great, open regions where matter has simply been scattered thin. The observable universe, remarkably, is not the whole universe. We can only see regions whose light has had enough time to reach us since the beginning of cosmic expansion. That visible region is what astronomers call the observable universe. It's genuinely enormous, and yet it isn't necessarily everything that exists. Beyond our own cosmic horizon, there may be considerably more galaxies, more stars, more dark matter, and more structure whose light simply hasn't reached us yet, and quite possibly never will. That boundary was never really a wall. It's simply a limit set by time, distance, and the ongoing expansion of space itself. Observers living in distant galaxies would have their own separate observable universes, each centered on themselves, overlapping with ours in some regions, and extending well beyond it in others. This idea genuinely changes the meaning of the word universe in everyday speech. What we can actually observe may be only one visible portion of a far greater whole. Space itself may even be infinite, well beyond our own cosmic horizon. Measurements suggest that the universe is very close to geometrically flat on the largest scales we can measure. If it's genuinely, perfectly flat, and if it extends without any true boundary, then space could plausibly continue forever in every direction, well past anything we could ever hope to observe directly. This doesn't mean infinite variety necessarily exists out there, since the same basic physical laws would likely still apply everywhere. But it does mean the raw scale involved may be far beyond anything the observable universe alone can suggest. Scientists remain genuinely careful here, since current data can't fully rule out other possible shapes for the universe, some of which would eventually loop back on themselves instead. Still, the leading picture points toward a truly vast, and possibly endless, expanse. Whatever the final answer turns out to be, it's a genuinely humbling thought. The boundary of what we can see was never necessarily the boundary of what actually exists. Let's pause once more and let your thoughts drift outward the way light itself drifts outward, patiently, endlessly, with nowhere in particular it needs to arrive. Let's turn now toward the countless worlds discovered around other stars, because the search for other planets has genuinely transformed astronomy itself. Not long ago, planets beyond our own solar system were only ever imagined. Now we know they're genuinely everywhere. Astronomers have discovered thousands of confirmed worlds orbiting other stars, with many more candidates still waiting to be studied carefully. Some were found because they tugged their host star slightly back and forth. Others revealed themselves by passing directly in front of their star and dimming its light by a tiny, measurable amount. These methods are genuinely delicate, and yet they've opened up an entire galaxy of new possibilities. We've found worlds larger than Jupiter, worlds smaller than Neptune, rocky planets, scorched planets, frozen planets, and entire systems unlike our own in almost every way. The night sky was never simply a field of scattered stars. It's filled with suns that may carry entire hidden families of worlds circling around them, quietly, the whole time. Some exoplanets orbit two suns at once. Science fiction pictured worlds with double sunsets long before any telescope confirmed such places genuinely existed. In some star systems, two stars orbit each other closely, and a single planet circles around both of them together. These are called circumbinary planets. Their skies would be governed by constantly changing light, shifting shadows, and seasons far more complicated than anything found here on Earth. The planet's own orbital path has to stay stable enough to avoid being flung away entirely by the combined tug of two separate stars, which makes systems like these especially fascinating to study. Some have been discovered simply by watching starlight dip in repeating patterns as a planet crosses in front of its two paired suns. The idea feels genuinely beautiful because it manages to feel both alien and understandable at once. A horizon light that could hold two dawns, two noons, and two fading lights at the end of the day, all guided together by gravity's own careful choreography. So-called hot Jupiters race around their stars in only a handful of days. Some giant planets orbit so close to their star that an entire year there lasts only a few Earth days. These worlds are called hot Jupiters because they resemble Jupiter in raw size, but live instead in truly blistering heat. Their atmospheres can swell dramatically under intense radiation, and some are even slowly losing gas out into space as a result. They were actually among the very first exoplanets ever discovered, since their gravity tugs strongly on their host star, and their large disks block a noticeable amount of starlight during a transit. Their existence genuinely surprised scientists at first. Giant planets were expected to form farther out from a star, where ices could help build up large cores over time. Hot Jupiters suggest instead that planets can migrate dramatically after forming, shifting inward through interactions with their surrounding disk or with other nearby planets. They reveal that solar systems aren't always neat, orderly, clockwork arrangements. Some are genuinely restless, rearranged, and extreme. Some planets, remarkably, run hotter than certain stars. A planet can become so intensely heated by its own star that its dayside temperature actually exceeds that of the very coolest stars known. These ultra-hot worlds typically orbit extremely close to bright, powerful suns, receiving relentless radiation the entire time. Their atmospheres can become so hot that molecules split apart entirely, metals vaporize outright, and powerful winds carry material from the day side over to the night side. On that night side, atoms and molecules may recombine again, releasing energy in strange, ongoing cycles of atmospheric chemistry. These planets genuinely blur the familiar boundary between an ordinary world and a star. They're not massive enough to sustain fusion the way a true star does, and yet their surfaces and skies can still glow with extraordinary heat regardless. They show that the word planet was never guaranteed to mean cool rock, pale cloud, or distant ice. Some planets are simply furnaces, forced into brilliance by the stars they orbit so closely. One distant world may genuinely rain molten glass sideways. One famous exoplanet is a deep blue giant, with weather that sounds almost impossible to believe. It orbits close to its star, where temperatures run fierce, and winds may race across the sky at thousands of miles an hour. Its blue color likely comes not from any ocean, but from tiny silicate particles suspended in its atmosphere. Silicates are the very same building blocks used to make ordinary glass. Under those extreme conditions, they may condense into droplets and fall through the sky, while violent winds drive them sideways as they fall. The image itself is astonishing, and yet it's genuinely grounded in real atmospheric science. Weather was never limited to water vapor and ordinary clouds, the way it is here on Earth. On other worlds, rain can be made of minerals, metals, or exotic chemistry entirely, shaped by heat and pressure. This particular planet is a quiet reminder that nature doesn't design its skies for comfort. It designs them from whatever ingredients happen to be genuinely available. Certain carbon-rich planets could plausibly hide vast interiors of diamond. Planets form from the surrounding chemistry present around their young star. If a given system contains more carbon relative to oxygen than our own does, some rocky planets there may develop genuinely different interiors as a result. Under sufficiently high pressure, carbon itself can form diamond. This doesn't mean a sparkling gemstone world, covered head to toe in jewels. The reality would be considerably darker, heavier, and stranger than that. Deep below the surface, carbon-rich layers could be compressed into vast, crystalline structures instead. Planets like this might have unusual geology, entirely different volcanic chemistry, and interiors unlike Earth's own silicate mantle. Scientists have already proposed a handful of genuine candidates, though proving their exact composition remains genuinely difficult from this distance. Still, the possibility alone changes how we imagine other worlds. Earth was built from one particular recipe. Elsewhere, the ingredients may vary enough to create planets where ordinary rock quietly gives way to carbon structures, formed under unimaginable pressure, hidden far beneath an alien surface. Ocean planets may exist too, covered by seas thousands of miles deep. Some distant worlds may contain far more water than Earth does. Instead of continents and shallow ocean basins, they could be wrapped entirely in global seas, extending down to genuinely incredible depths. At the surface, there might be waves, clouds, and storms, much like our own. Far below, though, pressure would become so extreme that water could form an exotic, high-pressure ice instead. Even while temperatures stayed warm enough for liquid layers above, this particular kind of ice wouldn't resemble a frozen pond here on Earth at all. It's a considerably denser form, created purely by crushing weight. The deepest ocean there might even be entirely separated from the planet's rocky core, which could affect both chemistry and habitability in turn. Still, worlds like this are genuinely fascinating because they expand our whole idea of what a planet can actually be. Earth has oceans resting on top of solid rock. These planets may be ocean first, with any rock hidden far below, almost like a distant, half-forgotten memory. Super-Earths are genuinely common throughout the galaxy, and yet entirely absent from our own solar system. Many exoplanet systems contain worlds larger than Earth, but smaller than Neptune. Astronomers call these super-Earths when they appear to be likely rocky, or at least partly rocky in composition, though the name was never meant to suggest they're somehow better than Earth itself. Strangely enough, our own solar system contains none at all. We move directly from small, rocky planets to giant gas worlds, without anything genuinely in between. This absence makes our own system feel considerably less typical than once assumed. Super-Earths themselves can vary enormously. Some may carry thick atmospheres, some may be genuinely ocean-rich, and others may be rocky and blisteringly hot instead. Their gravity would run stronger than Earth's own, and their geology could follow entirely different patterns as a result. Because they're so common around other stars, they may hold important clues about exactly how planets form and migrate over time. The universe, it seems, builds many worlds in a particular size range our own neighborhood somehow simply skipped. Rogue planets, drifting freely with no star at all, may genuinely outnumber the stars in our galaxy. There may be countless planets moving through space, without ever orbiting a single star. Some were probably born inside an ordinary planetary system and later thrown out entirely by a gravitational encounter. Others may have formed entirely alone from a small, independently collapsing cloud. Since they don't shine by reflected starlight in any ordinary way, they're genuinely difficult to detect from here. Astronomers find some of them through a technique called gravitational microlensing, when a wandering object happens to briefly magnify the light of a more distant star passing behind it. These worlds could be frozen on the outside, and yet the very largest among them might retain internal heat for remarkably long periods of time. A few might even hide a subsurface ocean beneath a thick shell of ice. If rogue planets really are as common as some estimates suggest, the galaxy isn't only a place filled with stars and orderly solar systems. It's also filled with dark travelers, moving quietly between them, entirely unseen and unclaimed. Some planets could genuinely orbit inside the habitable zones of red dwarf stars. Red dwarfs are small, long-lived stars, and many of them appear to have planets of their own. Because they're so dim, their habitable zones sit unusually close in, where a planet could plausibly receive enough warmth for liquid water under the right conditions. This makes them exciting targets in the ongoing search for life elsewhere. Close orbits like these bring their own complications, though. A planet may become tidally locked, with one side always facing the star directly. Red dwarfs can also produce powerful flares, which may strip away a planet's atmosphere or bathe its surface in harmful radiation. Even so, an atmosphere or an ocean could help move heat around the planet, and magnetic fields or unique chemistry might offer some genuine protection in turn. Systems like these are worth studying closely, precisely because red dwarfs are so abundant throughout the galaxy. If even a small fraction of their planets remain genuinely habitable, the galaxy could contain a great many small worlds, quietly circling faint red suns, patiently waiting in their own dim starlight. Let's rest here again for a moment. Let your breathing settle the way a distant planet settles into its own steady orbit, patient, quiet, entirely unhurried by anything at all. Let's turn, finally, toward the instruments and missions that let us glimpse all of this from here on Earth, because the tools themselves carry their own quiet wonder. The James Webb Space Telescope actually unfolded like origami once it reached space. It was simply too large to launch already assembled in its final shape, so engineers designed it to fold up neatly inside a rocket instead. After reaching space, it performed an incredibly careful sequence of deployments. Its sunshield stretched open in layers, each one thinner than a single human hair, despite its overall broad size. Its golden mirror unfolded from several segmented pieces into one single, continuous observing surface. Every single step had to work with extraordinary precision, far from any help on Earth. The telescope then traveled to a stable observing position, where it could stay cold enough to detect faint infrared light reliably. Webb is remarkable, not only for what it actually sees, but for how it became itself after launch. It was a machine, packed carefully like a folded promise, then finally opened out in space, into one of the most powerful eyes humanity has ever managed to build. Webb can study starlight filtered directly through alien atmospheres. When a planet passes in front of its own star, a tiny portion of that starlight travels straight through the planet's atmosphere, before ever reaching us here. Molecules in that atmosphere absorb specific colors of light as it passes through. By studying exactly which colors are missing, Webb can identify gases like water vapor, carbon dioxide, methane, and other compounds present. This particular technique, called transmission spectroscopy, lets scientists investigate worlds far too distant to ever visit directly. The measurements themselves are genuinely delicate, since the signal involved is small, often buried deep inside the bright glare of the host star. And yet, with enough careful observation, an atmosphere slowly begins to reveal itself regardless. We can't stand on these distant planets, feel their air directly, or watch their clouds firsthand. Still, their skies can leave real fingerprints in light, and those fingerprints can cross the vast distances of space to tell us exactly what they're made of. Hubble revealed entire galaxies in patches of sky where darkness once seemed completely empty. In the 1990s, astronomers pointed Hubble at a tiny patch of sky that looked almost entirely blank. The telescope stared patiently for days, slowly collecting faint light. The result was genuinely astonishing. That seemingly dark, empty-looking region turned out to be filled with galaxies, each one containing billions of stars of its own. Later, even deeper field images reached considerably farther, revealing galaxies from even earlier cosmic times. These observations changed the emotional scale of the entire universe. A speck of apparent emptiness became a genuine window into thousands of separate star systems and billions of years of cosmic history. Hubble showed clearly that darkness in the sky often simply means our own eyes aren't sensitive enough to see what's really there. The universe is considerably richer than casual sight alone would ever suggest. What seems entirely empty may actually be crowded with ancient light, patiently waiting for a sufficiently patient telescope to gather it in, one photon at a time. Radio telescopes can genuinely listen to cold hydrogen drifting between the stars. Space contains enormous clouds of hydrogen gas, much of it far too cold and faint to see with any ordinary optical telescope. But neutral hydrogen emits radio waves at one particular wavelength, roughly 21 centimeters long. Radio telescopes can detect this specific signal and use it to map gas across entire galaxies as a result. This has revealed spiral arms, rotating disks, tidal streams, and hidden structures extending far beyond any visible starlight alone. Hydrogen itself is the raw material stars are eventually built from, so tracking it carefully helps astronomers understand galactic growth and the future birth of new stars. Radio astronomy also works straight through dust that would otherwise block visible light entirely, letting scientists study regions that would otherwise stay completely hidden from view. In a genuinely poetic sense, the coldest gas in all of space has a voice entirely its own, not sound moving through air, but a quiet radio whisper, carrying the shape of galaxies across unimaginable distance. Space probes have actually touched the sun's own outer atmosphere directly. The sun seems entirely unreachable from here, and yet a spacecraft has genuinely flown through part of its outer atmosphere, called the corona. The Parker Solar Probe was built specifically to survive intense heat and radiation, while passing closer to the sun than any previous mission ever attempted. Its heat shield protects delicate instruments, as the spacecraft samples particles and magnetic fields near our own star directly. The corona itself is genuinely mysterious, since it runs far hotter than the visible surface sitting directly beneath it. By flying straight through this region, the probe helps scientists understand solar wind, magnetic activity, and the processes that affect space weather throughout the entire solar system. This matters enormously for satellites, astronauts, and power systems here on Earth. The mission is daring in a very literal sense. Humanity built a machine that can skim the very atmosphere of a star and return real measurements from the edge of fire itself. Voyager 1 carries human sounds far beyond our own solar system, even now. Launched in the late 1970s, it traveled past the giant outer planets and continued outward into genuine interstellar space. Attached to it is a golden record containing greetings, music, natural sounds, and images, all carefully encoded as information. That record was never meant for any likely recipient arriving soon. Space is simply too vast, and the chance of it ever being discovered is genuinely small. And yet its meaning remains profound regardless. It's a symbolic message from Earth, carrying ocean waves, wind, heartbeats, birdsong, human voices, and music out into the dark, endless space between the stars. Voyager 1 is now far beyond every planet, still sending faint signals back across billions of miles of empty space. Its instruments will eventually fall silent, but the craft itself will simply keep moving regardless. A small, human-made object will keep drifting quietly through the galaxy, carrying traces of the world that first launched it, for as long as it continues to exist. New Horizons revealed Pluto as active, complex, and genuinely strange once it finally arrived. Before that spacecraft got there, Pluto remained mostly a blur, even to our most powerful telescopes. The flyby changed all of that forever. Its images revealed mountains of water ice, smooth plains of nitrogen ice, layered hazes, dark equatorial regions, and one bright, heart-shaped basin. Some surfaces appeared surprisingly young, with very few craters, strongly suggesting real, ongoing geological activity. Scientists saw possible ice flow, cellular patterns within its frozen plains, and genuine clues to a complex atmosphere, slowly escaping into space. Pluto became considerably more than a distant point marked on a chart. It became a real, tangible world with genuine landscapes, weathering, and its own history. The encounter also reminded us just how much can remain hidden until we actually go and look directly. A small dwarf planet, long treated as simple and entirely frozen, turned out to be one of the most visually and scientifically surprising places humanity has ever visited. Asteroid samples, brought carefully back to Earth, can reveal chemistry older than our own planet. Some asteroids preserve material from the very earliest solar system, dating back before the planets ever fully formed. When a spacecraft collects samples and returns them home, scientists can study individual grains, minerals, and organic compounds using laboratory tools far more powerful than anything ever flown in space. These samples may contain tiny particles genuinely older than our own sun, along with chemistry that records conditions present in the early solar nebula. They can reveal exactly how water-bearing minerals formed, how carbon-rich compounds got distributed, and how small bodies contributed raw ingredients to young, forming planets. Unlike ordinary meteorites found on the ground, these carefully returned samples can be protected from contamination and linked directly back to a known asteroid of origin. Each individual speck is genuinely precious, since it carries information from a time before Earth ever had oceans, continents, or open skies. Holding a piece of asteroid material is a little like touching an actual fragment of the solar system's own beginning. Future telescopes may eventually search nearby worlds for genuine signs of life. The next great question isn't only whether other planets exist, but whether any of them are actually alive. Future observatories may study rocky worlds around nearby stars with enough precision to search directly for atmospheric clues. Gases like oxygen, methane, carbon dioxide, and water vapor can mean many different things on their own, so scientists will need to interpret them with real care. A genuine biosignature would likely come from patterns that are difficult to explain without biology, considered carefully alongside a planet's star, climate, and geology together. This search will be slow, cautious, and genuinely extraordinary. We may never find forests, oceans, or creatures directly. We might simply find a subtle chemical imbalance, quietly present in a distant atmosphere. And yet, even that alone would be enough to change human history entirely. A single faint signal from another world's atmosphere could suggest that life was never unique to Earth after all. Outer space, again and again, keeps proving that reality is stranger than imagination ever managed to guess. The universe has consistently exceeded the stories humans first told about it. We imagined the stars as distant, fixed lights, then eventually learned they were suns of their own. We imagined planets as genuinely rare, then found them practically everywhere we looked. We pictured space as simply empty, then discovered fields, radiation, dark matter, and structures larger than anything the eye alone could ever grasp. Each new generation of instruments reveals something stranger still: moons with hidden oceans, black holes with measurable shadows, entire galaxies from the earliest cosmic dawn, worlds where glass, methane, metal, or ice might genuinely shape the weather. The wonder here was never that science slowly removes mystery from the world. It deepens it instead. Every answer opens a wider question, and every distant signal reminds us that nature is considerably more inventive than our own first guesses ever managed to be. Outer space was never simply far away. It's the grandest reminder we have that reality still holds real surprises left. Let's slow all the way down now and gather the vast, gentle picture we've built together tonight. We wandered from the very first stretching of the universe, all the way to ancient light still quietly drifting through every corner of the cosmos tonight. We followed stars through birth, fire, collapse, and brilliance, one after another. We passed black holes where time itself bends, moons hiding entire oceans, planets with no sun at all to call their own, and galaxies slowly gathering together across the dark. We saw that space was never truly empty, but alive instead, with motion, radiation, gravity, dust, and distant signals, quietly passing through it the whole time. Even in the silence between worlds, something is always unfolding, somewhere. And perhaps that's the real comfort tucked inside all of it. The universe is vast beyond ordinary measure, and yet it was never still. It's moving, changing, glowing, and becoming, in rhythms far older than any single worry you happen to be carrying tonight. So now, let those thoughts drift a little farther away. Let the planets turn without needing your attention at all. Let the stars burn softly on, somewhere out in the distance. Let the moon continue along its own slow, patient path. And let the deep sky hold every remaining question for a while, so you don't have to. Let your own breathing settle into that same unhurried rhythm now, the one every star, every planet, and every quiet galaxy has already been following, long before you ever arrive to notice it. There's nowhere you need to be, and nothing left to solve before sleep finally comes. Let your shoulders soften completely. Let your thoughts grow light and spacious, like starlight quietly fading at the very edge of sleep. Rest now. You've earned it. Good night.